Bonjour, alors on reprend après le mois de Ramadan. Tout d'abord, j'en ai voulu concerner 2 semaines pour les réponses par rapport au Homework One. Alors, ce sera sur 2 parties, cette semaine et la semaine prochaine. Et de suite, on continue avec le livre de Monsieur Nio. Alors, euh, donc, les notions de edge distance, pitch, etc. C'est ce qu'on va voir dans cette semaine. Alors, edge distance. Edge distance is the measurement from the center of a fastener, rivet, bolt, hole to the nearest edge of a material. It is crucial in engineering to prevent material cracking, fastener failure, or structural weakness under load. Typically required to be at least 1.5 to 2.5 times the diameter of the fastener. So, edge distance, it's a measurement. It's defined as the perpendicular distance from the center of the bolt hole to the nearest edge of the plate. In a joint, each part has its own edge distance. Significance. Ensures the structural integrity of joints, particularly in steel structure and aircraft skins, by preventing edge tear out. Typical requirements in aerospace, a common rule is 2 times or 2.5 times the rivet diameter, which allows for future oversizing without damaging the part. Proper edge distance ensures that the surrounding material has sufficient strength to hold the fastener, particularly under heavy structural loads. As seen as we said, picture, the edge distance is critical, a critical notion, as for the joint bearing failure, as seen in this picture, or for the tear out failure. At the right hand, you can see the edge distance, and just above the edge distance definition, you can see why it's crucial for engineering to prevent material cracking. So the notion of edge distance is important. The next one is pitch, and pitch is the distance between the centers of two rivets or bolts located in the same row. The low pitch is a joint. No, the low pitch it's not a joint. I mean, the low pitch in a joint is critical for fatigue concentration factor, and long pitch is critical for inter-rivet backlink. For the static inter-rivet backlink. For the static, yeah. So, at the picture just below the description of pitch, you can see that we need to maintain 4D at minimum 4 times the diameter as a pitch distance. As much as it's short, it's critical for fatigue. As much as it's long, it's critical for the static, for inter-rivet backlink. So, the next one is mechanical stiffness. Mechanical stiffness is a measure of a structure's or material's capacity to resist elastic deformation, bending, stretching, or twisting when subjected to an external load. It is calculated as the ratio of force applied to the resulting deflection with stiffer materials displaying less deformation under the same force. Definition: stiffness is the resistance of a component to deformation. Elastic behavior: it describes behavior within the elastic range, meaning the component returns to its original shape after the load is removed. So what's stiffness vs strength? Stiffness is not strength. A stiff material like glass can be brittle, fragile, while a strong material like steel can bend significantly before breaking. So material vs structure: while dependent on the Young's modulus, structure stiffness also depends on geometry, example the shape, the thickness. The formula often defined as K, the stiffness, is equal to the load F divided by the displacement delta. So types of stiffness like axial stiffness: resistance is resistance to pulling or pushing. Bending stiffness is resistance to bending, dépliage to pliage, to the resistance to bending moments, to ce qui est pliage. Torsional stiffness is resistance to twisting. The last notion that we're gonna talk about it this week is stress concentration factor. What's the definition and formula of stress concentration factor? The theoretical stress concentration factor for normal stress is defined as the maximum stress divided by the nominal stress at the critical section. The physical meaning: when a structural component has discontinuities like notches or holes, the lines of force stress flow become crowded. The stress flow become crowded, resulting in a higher localized stress concentration in that region. The geometric dependence is like the KT, the stress concentration factor, is highly dependent on the geometry, such as the ratio of the fillet radius to the width of the part, with smaller radii causing higher concentration. So methods to mitigate stress concentrations. To reduce high stress concentration factors, methods to mitigate stress concentration. The last notion that we're gonna talk about it this week is stress concentration factor. What's the definition and formula of stress concentration factor? The theoretical stress concentration factor for normal stress is defined as the maximum stress divided by the nominal stress at the critical section. The physical meaning: when a structural component has discontinuities like notches or holes, the lines of force stress flow become crowded. The stress flow become crowded, resulting in a higher localized stress concentration in that region. The geometric dependence is like the KT, the stress concentration factor, is highly dependent on the geometry, such as the ratio of the fillet radius to the width of the part, with smaller radii causing higher concentration. Material independence. Theoretical KT depends solely on geometry, not on the material itself, so the actual effect on the material depends on its elasticity. Causes. Common causes of high stress concentration factors include sudden changes in cross-section, like sharp corners, holes, keyways, and scratches. To reduce So methods to mitigate stress concentrations. To reduce high stress concentration factors, designers often use methods to make the transition smoother, such as adding fillet ready to sharp corners, like you see in the picture at the left. The abrupt change stress flow lines are crowded and high stress concentration is presented, while the smoother change with the fillet there's a smoother change and the flow lines less crowded. Like this you have lower stress concentration. So the methods to mitigate stress concentrations is to adding fillet ready to sharp corners, enlarging holes, or adding small relief notches to redirect stress flow away from critical areas. So that's all for this week, and next week we're going to talk about the part 2, where there's the definitions with their mathematical formulations for shear, shear out. Shear out we already spoken about it in the first answers for the part 1 of the shear out and the bearing also. So we're gonna talk next week about tension and direction shear tension, beam bending, the case of shimming, enfolding, inter-rivet buckling, Heth theory. That's it, and have a nice week.